Yes. Mm. Well, welcome this afternoon. Um, I can skip the introduction. You have just heard who I am. But it's about a project for long-term low-cost monitoring. Okay. Mhm. Okay. Found it. So, as you have already heard, so the cost is a major issue in the monitoring major challenge for large-scale CO2 storage. And what you see here is an aerial view of Calgary and some different outlines of plumes of various size, of various volumes overlain. In the middle, there's 10 megatons, and then on the outside here, you have 1 gigaton. And the diameter of the thing here is 75 kilometers. As you can imagine, uh, conventional 2D or 3D seismic surveys will be quite costly and also quite impractical, especially if you think about on land, you may have houses, towns, infrastructure, um, um, and you may not be able to you can reoccupy certain areas. Offshore, you have traffic, you have oil and gas rigs, um, wind farms, and other things that are obstacles. Also, so we don't only need to kind of monitoring during when the CO2 injection is going on, so for kind of, decades, but also after CO2 injection has ended, in Norway up to 20 years. So um, I mentioned the project already. It's an ACT4 project, SPARSE. SPARSE is short for Sparse Passive Active Reservoir Monitoring using seismic electromagnetic gravity and surface deformation. We have a lot of partners from Canada, the NVS, UK, France, and from Norway. It's a node-based monitoring, and if you look at this image here, so we have this is obviously an offshore case with a seafloor. We have in the overburden. So here we have a reservoir with a CO2 plume. We have a larger pressure plume, and you may observe some microseismic vents. We also may observe some surface deformation due to the pressure. And the idea is now to have some nodes at the seafloor where seismic, EM, sources and receivers are combined, uh, and then with some gravimeters and other acquisition equipment. To monitor from this node basically what's underneath the node. So it's it's spatially very sparse, but in time very high resolution. Kind of monitoring with highly repeatable geophysical data. And the nodes, so the idea is to have them strategically distributed. For example, here you have an injection well. You have, for your conformance monitoring, you have an expectation where your plume will go. And then you can use these nodes to determine if you have conformance or not. And if not, you at least know where. So if you need to go in and if this will trigger an active survey, you know when and you know where. So you can limit the amount of monitoring that you might need to do that. Okay. So the idea is to establish a principal node design. So we don't produce a prototype because there's no one size fits all. We have to adapt the node design to the site that we're monitoring. But we're producing a toolbox. Toolbox meaning both geophysical methods that are applicable to nodes in different configurations, and then also workflow that tells us how to assemble a kind of node-based monitoring system for a certain site. And the prerequisite is that it's low cost and it's also practical. That's very important. So we're looking at a couple of different components here. One is the geophysical monitoring. So we have different methods that we are using. As I mentioned, seismic, EM, gravity, and so on, surface deformation. But what we need to do is to actually, so we need to establish conformance. That means, so we need to go from our geophysical measurements to consideration and to pressure. And since we have only a few data, we need to extract the maximum amount of information from the data that we have. Um, so I already mentioned, so we also need to quantify the key parameters for the conformance, and then also the technical realization. This has also an influence on what kind of methods we can use. So so we don't, or so we want to base this monitoring system on existing technology. So so that everybody can go and buy what they need to establish this monitoring system. So the question, what kind of sources receivers are there? What do they cost? What other equipment is there? What can we use? Also, so how is the node designed in general? What kind of offsets can we have? But also, how is the nodal system designed? So what's the optimum positioning? How many nodes do you need? And also, so we will do a kind of value information study here to see what makes sense and what doesn't. Important is also quite practical consideration. So how do we do the power supply? How do we do the data transmission? Do we need communication between the data, between the nodes? That will be quite important. Another thing, and that has been mentioned before, is automatization. So if we have a lot of data coming in, that will not work. So we have to have some pre-processing, some data reduction, ideally on nodes, and then and that's not part of this project yet, but this is a long-term view. So the kind of operator should get an email once a month with the key parameters and kind of a traffic light on there. As I said, not part of this project, but that's where we hope this will go at some point. Yes, and we're testing the different components at different scales. There are some examples for potential sparse active monitoring here on the left-hand side. The seafloor case, where the seismic sources and receivers will be on the seafloor. So we'll be doing some baseline monitoring, and then what is continuously, maybe every day, every week, every month, some monitoring. We will look at the difference over time and derive the conformance or from that. In the onshore case, a little bit more difficult because due to the high variations in the properties of the most shallow subsurface, you can have dry conditions, you can have quite wet conditions, freezing, and so on, and that will change your data. So the idea is to, for example, use steel piles to couple the source directly to the bedrock or your shallow wells. So we'll also look at the optimum offsets here. For the CCM case, that's down here, we're mostly looking at vertical sources or at the vertical component of the field, because that's mostly sensitive to kind of thin CO2 layers. Offshore, these will be on the seafloor. Onshore, they will certainly be in the wells. Some examples for potential passive seismic monitoring. So in the kind of passive arena, we will look at everything from microseismic to teleseismic. At the moment, we're looking at data from CAMI-FRS and ACT4. Also considering, of course, gravity. That's kind of a staple. Here's an example from Sleipner, so that has proven to work really well. Or surface deformation. That's an example here from INSAR using INSAR. Yes, some examples about data exploitation from our own Svelvik field lab. On the left-hand side, there's a example for extracting small changes of pressure from seismic data, and here it's quite nice. So when we inject CO2 at Svelvik at 65 meters depth, it's kind of migrating upwards, and we know where it's going because we have done this a couple of times. So we place the source here and receivers here, and we're now looking at kind of different ray paths. So this is the one through the seal. This is the waveforms over time. So this is time along the waveforms, and we see there's no change in the waveform in the seals, or as expected or as hoped. The spectrum, we also don't see a difference here. When we look at this ray through the plume, we see that in the beginning there's hardly any change, but suddenly we see a big drop in the waveform and also a delay in the first arrival times, and we see big changes in the spectrum. But yeah, the interesting thing is that not all so different parts of the spectrum see different things, and so we want to look a little bit further into that. And of course, we have to check then, do we see this also on large-scale data? Quantification is an important issue for the conformance assessment. So the traditional way is to go from geophysical data to geophysical images, for example, VP models, and then to do a represent version to go to CO2 saturation. Here's the relation between P-wave velocity and CO2 saturation, and you see a lot of different curves, and they represent different distributions of CO2. So going from homogeneous to patchy. And these are usually not known, but we can invert with it. So if we only use seismic data to invert for both, so like a Brie exponent, which represents those curves, and CO2 saturation, then we see there's a large range of uncertainty. But if we add kind of resistivity from CCM to the mix, then this uncertainty is hugely reduced. So I just mentioned that this kind of conventional approach, but we're also looking at direct approaches going directly from seismic data to CO2 saturation, negative pressure. Here's an example where we combine seismic data and EM data, and without any further inversion, so directly go to this to the parameters that we're looking for, and this of course lends itself quite well to kind of automatization. Important here is that we can extract enough information from the sparse data to keep the uncertainty small. We can achieve this by using multi-method, as you see here, seismic and CCM, for example, but also what I mentioned before in terms of data exploitation, that we extract as much information from the data as possible. In seismic, for example, I'm thinking at BP, VS, QP, maybe anisotropy as a measure of pressure. We can also use additional independent information, for example, surface deformation, microseismic events, and so on. Currently, there's some testing ongoing at the Kami field site in Canada. So we're looking at the different installation modes for those sources. I mentioned those steel helical piles, and the different sources being tested. For example, orbital kind of vibrator sources, which are the washing machine, which are these washing machines that Rick mentioned. Then conventional vibrators. We're looking at number sources, which basically an accelerated drop weight. So we're looking at the plasma source, and a little bit later we'll also look at an impulse source, so at a fuel-powered impulse source. We're also looking at how can we use DAS in the context of for node in terms of sensing arrays or small antennas. To sum up, so we want to establish SPART nodes for low-cost and long-term CO2 monitoring. It's intended for background monitoring, which may trigger then target-oriented service when and where needed. This may reduce or ideally even remove the need for costly fully 3D monitoring service. We develop a nodal system design which integrates geophysical monitoring, conformance assessment, implementation, and also keeping the cost in mind. We explore how to use the data optimally, and so we're also testing different components, both in terms of how to monitor, but also the hardware in the field on different scales. And with this, I would like to thank you.